Okay, so today we'll start by going through some stylized facts about how production works and how it grows. So to start, a production function maps vectors of goods used as inputs to vectors of outputs, things that we're producing. The inputs are typically called factors. Think of them as, like from the root fact, make, like a factory, but they're not multiplied together necessarily, like factors in math. So just don't get confused by that if you are new to this terminology. And for now, and indeed through much of the program, we'll be saying that there's just one output good for simplicity. It's denoted Y, and we can consume it or turn it into equipment to produce with later. But it's just this homogeneous thing. The more, the better. You can think of it as yummy consumption sludge. Aggregate production of Y is the amount produced throughout an economy given the vector of input quantities being fed in. So we're thinking at the aggregate level generally rather than like the firm level or the industry level. And again, for simplicity, we'll lump all the inputs into two categories: capital, denoted K, and labor, denoted L. So equipment and people get combined in some, firm to produce things. This production function F might be Cobb-Douglas. It might take some other CES form like we saw yesterday. It might take all kinds of forms. But what we'll really generally be assuming is that it's continuously differentiable and increasing in each argument. Note that capital is equipment used in production. It's not money. We won't really be dealing with money. It's just a thing, it's sort of a unit in the background to denote how much of a given input you can buy and how valuable what you're selling is. So note that as well. Now, another feature that those two production functions I just wrote down have is constant returns to scale, right? You see that I had, in general, a Cobb-Douglas production function could have the exponents on K and L being anything, but I've been having them add up to 1. So if you double the amount of capital and the amount of labor, you multiply output by 2. 2 to the A plus 1 minus A. And that is very widely assumed. The basic reason is the replication argument. If you imagine we doubled the Earth with all of its capital, including its land and natural resources, and all its labor as well, you just have double the factories, double the roads, double everything. Output would double. Now, this is holding technology fixed, right? If we really doubled the world and each planet could have its its scientists and engineers coming up with new ideas, new blueprints that could be shared across the worlds, then after some time had passed, you would expect output to be higher on each world than it would if the other didn't exist, right? So you get kind of increasing returns to scale over time. But holding technology fixed, the thinking is if you double the inputs, you just double the output. We'll be talking a lot about technological development and these increasing returns to scale later, but here we're just starting from the case of fixed technology. Now, even with fixed technology, you might expect a little bit of increasing returns to scale due to specialization, right? If there's some really long supply chain, people are making really, really specialized parts. Well, if you've got 20 billion people instead of 10, the whole, buy global economy can specialize more finely, and you can more than double output. But this is arguably a relatively minor effect at such a large scale. And a reason for thinking this is that the gains from trade that seem to be available to large advanced countries are usually estimated to just be a few percent of GDP. So, if France or something just cut off its borders, at least putting aside certain things they really seem to need to import, like oil and gas, um, then on typical estimates, output would probably not fall that much. Um, yeah, but you can dispute these estimates, but this is a common argument. Now, if we're just thinking about what would happen if you doubled the labor and accumulable capital, so not the land, right? But in practice, we're not doubling. We're not increasing the quantity of land really. As time goes on, we're increasing capital only by increasing the accumulable sorts of capital, the capital that past output can turn into new roads, new parts for factories, and so on. And so there might be decreasing returns to scale in labor and accumulable capital alone due to the fixedness of the natural resource inputs. But this is also typically estimated to be a small effect, at least at anything close to current margins. And this is because of the fact that the natural resource share is small. Well, we'll talk a bit about factor shares in a few slides, and you'll see why a small factor share probably means that that factor is not a huge constraint on growth. If the share is small, it's probably not imposing a big departure from constant returns to scale. And so if you think that these two effects roughly cancel out, then CRS is a decent first approximation to aggregate production as a function of labor and capital, or at least accumulable capital. Now, a really nice feature of assuming constant returns to scale is that it provides us with an easy answer about who gets paid what. This will turn out to just be really convenient all over the place, to the point that it's maybe a reason to be skeptical that constant returns to scale actually is what obtains, because the economic theorist is so desperate for it to be true. But anyway, the reason why it works is because of a theorem called Euler's homogeneous function theorem. The theorem says, let's say you have a function that's continuously differentiable and homogeneous of degree k. Homogeneity of degree k means that if you multiply all the inputs by some common factor, some m, now I'm using the term factor in the mathematical sense, the common coefficient m, then output will be multiplied by m to the k. Okay. So if the function is homogeneous of degree k, then if you go through all the factors and for each, or all the inputs to the function, and you multiply the level of the input, that xi there, by the derivative of the function with respect to that one input, and you add that up across the inputs, what you get is k times the level of the function at that vector of inputs. So if our production function is constant returns to scale, it's homogeneous of degree 1, right? If you double all the inputs, you double output, and this is the m equals 2 illustration. And here's what that means. So let's say the economy is perfectly competitive, meaning that the amount that each factor gets paid, like the total wage bill and the total amount collected in interest on capital investments, will equal the marginal product of that factor times the quantity. So each unit gets paid its marginal product. The intuition for this is pretty straightforward. If you're working and you're getting paid less than your marginal product, then you can take your labor elsewhere. You're providing a lot of value to the firm. Why aren't you getting compensated for that? You should be able to find some other firm that will pay you what you're adding, more or less. And why would anyone pay you more than your marginal product? So given competitiveness, the marginal product of capital and labor should be the interest rate and the wage rate, respectively. And so the total payments to capital and labor, as I was saying, will just be the quantity of capital times the marginal product, and the quantity of labor times its marginal product. And by Euler's theorem, when you add up these two things, you're just going to get output. You see that? We just have two inputs, little n is 2 here, and we're just adding up the quantity of labor times the marginal product plus the quantity of capital times the marginal product. K is 1 by constant returns to scale. So that tells us where all the output goes, how much goes to all the workers and how much goes to all the investors who own the capital. To see what goes wrong if we try to assume competitive factor payments, but we don't have CRS, for simplicity, let's just think about the single factor case. So let's say output's just produced by labor. In a world of decreasing returns to scale, if everyone gets paid their marginal product, everyone gets paid the slope of this line here, this tangent to the production function, and multiplying that by the number of people, you get total wage payments, and that'll be less than total output. And this raises the question of what happens to the rest of it. And likewise, if there's increasing returns to scale, if there's some projects that become possible because lots of people work on them that wouldn't have been possible if any individual had dropped out, everyone on the margins responsible for the whole project, or for sort of dramatically increasing the quality of the output. But you can't pay everyone that single thing that they all collectively produced. If you tried, total payments would exceed total output. And this raises the question of how you make up the deficit. So let's say that we do have CRS and capital and labor have their prices, and some firm has a budget B to invest so as to produce as much output as possible. Note how analogous this is to the question we were considering last time of how an individual with some budget can sort of produce as much utility as possible, as it were. In particular, given a constant returns to scale production function, this will be exactly analogous to utility maximization under homothetic preferences. Now here, the thing we're maximizing, output, is more sort of naturally, straightforwardly cardinal than utility is, right? If you have double the apples, you can just count the apples. It's obviously it means something to say that you've got twice as much, in a way that it isn't always so clear that it does when you're talking about utility. But the same optimization techniques are going to apply. It's still going to be the case that when solving for the optimal allocation of a firm's budget, you can take a monotonic transformation of the production function, because whatever maximizes some function will also maximize a monotonic transformation of it. Now, given two-factor production, as we've been working with, we can denote the elasticity of substitution between the factors locally around some price vector P by epsilon of P. And as usual, if that elasticity of substitution is greater than 1, then an increase to the relative price of labor will mean that relatively less is spent on labor. So the factors are easy to substitute for one another. So if the price of labor goes up, relatively speaking, the quantity that the firm will employ doesn't just fall, but it falls by a larger proportion than the price rose. And so the total amount spent on labor relative to capital falls. Now, we can think about this in reverse. Instead of thinking about what happens to the quantities employed when the prices change, we can just observe, well, given that we just have some stock of capital and labor today, which will be employed somewhere, everyone's going to basically work a full-time job, more or less. All the capital will be put to some use. So in equilibrium, the aggregate quantities purchased are going to be the stocks, K and L. We can ask what happens to the prices if the quantities change. And just sort of working through the algebra in reverse, if the capital to labor ratio rises by 1%, say, some small proportion, the relative price of capital will have to fall by 1 over the elasticity of substitution percent. That's the amount the price has to change such that, the firms want to buy for the same amount of capital as before, or relative to labor. This kind of gives us a really a really direct connection between elasticities of substitution and how prices affect factor shares. So the capital share is the fraction of output that gets paid as capital rents. Likewise, the labor share is the remaining fraction, the total wage bill. And we'll let the capital share be denoted alpha. As we've seen, in a competitive economy, the capital share will be the total amount paid for the use of capital, which is the quantity times the price, which will be the quantity times the marginal product. That's the total bill. And then you divide that by output to get the share, the capital share. You do the same thing for labor. And of course, given constant returns to scale, and given that these are the only factors, these are going to sum to 1. And as we can see, if the elasticity of substitution is greater than 1, then an increase to the capital to labor ratio of 1% is going to increase the capital share because capital becomes more plentiful and its price falls, but it doesn't fall by as much as the quantity grows more plentiful. Whereas if the goods are not so substitutable, if the elasticity is less than 1, the reverse happens. When capital becomes more plentiful, the capital share falls because the price of capital is falling more quickly than the quantity is rising. The edge case is the Cobb-Douglas case, where the share doesn't depend on the quantities. And as for what the share is, well, conveniently, it'll just be the exponent. So the capital share, alpha, will equal the quantity of capital times the marginal product of capital. We're just differentiating output with respect to capital. We pull the A down from the exponent, subtract 1. And this K cancels with the -1 up here. And what we're left with is just output, which we're dividing by to get the capital share. So that A we pulled down from the exponent is all that remains. So to look at the shares, to define the shares, we just need to look at the exponents. Often, a Cobb-Douglas production function is written with alpha and 1 minus alpha as the exponents. But I'll try to be consistent about using alpha to denote the capital share itself, and little a to denote the actual shape of the production function, the shape of what production makes possible, such that they're equal to each other under some assumptions, under perfect competition and so on, but not by necessity. Now, suppose that our production function looks like it looked before, but we introduce these factor augmenting technology terms, A and B. So production is now a function of what we can call effective capital and effective labor, rather than just capital and labor. What it means to double, say, B, labor augmenting technology, is that if we fix the amount of capital, we now need half as much labor as we needed before to produce any given quantity of output. Naively, just looking at a function like this and imagining an increase to B, that seems to evoke an image of workers sort of doing whatever they were doing before in the same capital environments that they were in before, the same factories or whatever, but just buzzing around twice as fast. Of course, that can happen, but in practice, increases in labor augmenting technology usually mean reorganizing production in a less labor intensive way. So you're now using your capital in a very different um, arrangement. So, for instance, consider the move from hand drawn to digital animations. Suppose the quality of the movie that they're making is the same, um, but it's just now being done on computer. If digital animations require 1/10 as many people to make the same movie, but each one needs a computer costing as much as the paper and ink that 10 hand animators had used, then A is unchanged. To make the movie, you still need as much capital as before. But B has grown by a factor of 10. Now, the people look about the same as before. We still have our brains looking the same and our 10 fingers and 10 toes. What's really changed is the capital, right? A computer is a very different thing from a bunch of paper and ink. But in this reduced form sense, what's changed is the level of labor augmenting technology. And A has stayed the same. Observe that if we're not thinking about A and B changing over time, but we're just talking about changes in the quantities of capital and labor at a given time, we can ignore the A and the B. We can just roll them into the shape of the production function, and that'll sometimes be convenient just to make things simpler. But it also reveals that if your production function was constant returns to scale before you thought about factor augmenting technology, it'll remain constant returns to scale, right? Double the K means double the AK, and so on. Another kind of technology, an even simpler kind, sometimes introduced, is total factor productivity, or TFP. This is just a coefficient on the whole production function rather than on one factor or the other. But if the production function is constant returns to scale, and we've already introduced terms for capital and labor augmenting technology, having a TFP term as well, a P as I'll denote it, is redundant. Because we can just, if we have a P on both inputs, we can just pull it out by constant returns to scale. Likewise, we can just push it in, which is to say that instead of talking about growth in P, we can just talk about A and B growing simultaneously at the same rate. In the Cobb-Douglas case, and only in the Cobb-Douglas case, we can dispense with particular factor augmenting technology terms and just use that TFP term for simplicity. So, the thing that you can just pull out and that turns into P will be the big A to the little a times big B to the 1 minus little a. And yeah, it won't make a difference whether technological development is written down as being labor augmenting or capital augmenting. It's all just the same thing. More generally, even outside the Cobb-Douglas context, it's standard to refer to this quantity TFP growth, which we can just define to equal the share weighted average of the growth rates of labor and capital augmenting technology. Note that this is not the same as saying that there's always some variable TFP, some well-defined quantity that, say, equals, like the analog to 6 here, with the shares replacing the A in the exponents. And this is because the shares are not a constant here. Alpha can change over time. Outside the Cobb-Douglas case, A itself could have a non-zero derivative. Alpha itself could have a non-zero derivative at a given time. So if you're just taking the growth rate of this term, it won't generally equal TFP growth. You would need to account for the changes in the alphas. something I'll cover a bit later is how to think about manipulating growth rates like this, how to work out what the growth rate of some variable is when you know the growth rates of the the various inputs to the function that generates the variable. But briefly, for those who are familiar with this sort of thing, I'll just note that in the Cobb-Douglas case, given this constant capital share equaling little a, you can easily work out what TFP growth is given observed growth rates in output, capital, and labor, right? So because y will take this form here, p times k to the little a, l to the 1 minus a, the growth rate of y will look like this. And then rearranging, you get the growth rate of TFP is the difference between the growth rate of output and the sum, the share-weighted average, really, of the growth rates of the inputs. That residual, the kind of unexplained growth in output, the extent to which growth in output exceeds the share-weighted average of the growth rates of the inputs, is going to be TFP growth. But this holds in general, given perfect competition. So GP, this thing here, will always equal this expression here, at least given that factors are being paid. Given that the sum of the anyway, at least given constant returns to scale, but more precisely, I should say, given perfect competition. Suppose there are n factors. We'll denote them f sub little I with factor augmenting technologies AI. And let big F sub I denote the effective quantity of factor I. We can denote the share of I at t by alpha IT. Now we can consider the impact on output of growing the quantity or the productivity of a factor for a given factor. So given perfect competition, as we've seen a few times now, I's share at t will be its marginal product times its quantity divided by well, actually, no, this is a little bit different from what we've seen. Its share will be the marginal product of an effective unit of the input times the effective quantity divided by total output. You can work through this if you're not convinced, but you can just imagine, well, what's the marginal product of a given unit? And then, that'll be multiplied by A, because, if the marginal product of a given unit doubles when A doubles, right? So when you take the derivative of the production function with the technology term on it, the technology term will show up in the derivative. And then you want to multiply by the quantity. The effective quantity is going to have that A in it. So the marginal product with respect to the a unit of like effective labor, say, if A is 2, that's going to be double the marginal product of labor itself. So this will be half as big as the marginal product of labor. The marginal product of effective labor is going to be half as big as the marginal product of labor, and then you're multiplying it by something twice as big, which is effective labor. So this will be the labor share if I is labor. And rearranging, you get this term here, which is maybe easiest to interpret if you just divide top and bottom by dt. So we're looking at the growth rate of output at t divided by the growth rate of effective labor or whatever at t. And rearranging, this says that the growth rate of output is going to be the share of I times the growth rate of effective labor at T. And you can split this apart into the growth rate of the labor augmenting technology at T and the growth rate of the quantity. So holding all else fixed, the growth rate of output induced by an increase in effective labor is just going to be the labor share times the growth rate in the quantity of labor plus the growth rate in its productivity. And if multiple factors are growing simultaneously, then you can just add all that up, and the result will be the growth rate of Y. So that's kind of an overview of production and productivity. Now for some stylized facts about how it seems to actually have unfolded, how production has grown over the last maybe century and a half or more in the developed world. So back in 1957, Nicholas Kaldor published a list of macroeconomic regularities that seem to more or less hold throughout the developed world, at least if you zoom out enough, if you kind of average decade by decade or so. He called them stylized facts. And in fact, I think he coined the term stylized facts to refer to them. And at least to my mind, they've held up surprisingly well over the many decades since. The first is that output per person grows at roughly a constant rate, about 2% a year. The second is that the interest rate, that is, assuming perfect competition, the marginal product of capital, is about constant, maybe 5% a year. Now, here we're talking about what the risk-free interest rate would be in a risk-free world. And of course, in practice, every investment has its own risk profile, and there are lots of different interest rates. But for the purposes of the stylized facts, we can go with an interest rate of, say, 5%. And the third is that the capital to output ratio is constant. That is to say, the value of all the capital equipment we have lying around at a given time is usually about the same multiple of how much we're producing in that time. So in a given year, say we're and the ratio is about 6. So the value of all the factory parts and all of that is about 6 times GDP. Now, just these 3 facts turn out to have surprisingly many implications for how growth currently seems to work in the industrialized world. And of course, we're going to be thinking about what happens when the world changes a lot and, seeing what could cause these facts to change and how radically they could change. But before getting there, it's good to see, how things work already and why, if nothing else, why models are typically written the way they are and why people tend to think the way they do. So we'll be pulling a bunch of rabbits out of hats here. We're going to be showing that these 3 facts have implications for all sorts of domains that seem potentially a bit disconnected from them. The first, and maybe closest to home, is what they imply for the capital share. They imply that the capital share should be constant. Why is that? Well, remember the capital share is the marginal product of capital times the quantity divided by output. And just cutting up this expression slightly differently, you've got the marginal product of capital, which is going to be constant, times the capital to output ratio, also constant, by facts 2 and 3 respectively. And if the first thing, the interest rate, is around 5% and the second is around 6, then you would expect, on looking it up, to find the capital share constant at around 30%. And sure enough, the capital share is roughly constant at around 30%, or maybe a bit more, a third or something in that ballpark. The labor share, of course, has been the rest, about 2/3. People often make a big deal about how this fluctuates, and maybe over the last decade or two in the developed world, maybe especially in the US, the capital share has risen a bit. Now it's maybe closer to 40% than to 30. And that might be true and important for some purposes. But to my mind, the more fascinating thing and kind of fundamentally important thing to realize is how constant it's been, even as so much else about the world has changed. Over 100 years and more, we've moved from having majority of people working in agriculture to less than 2%. We've had the whole revolution in computing and telecommunications. We've had women entering the workforce in a really big way, and yet the capital share has hardly changed. Now, before going further and trying to pull any more rabbits out of hats, let's just get back to developing our intuition about how exponentials work in general. Because, of course, especially for part one here and how it'll sort of infect everything else, we'll be dealing with exponential growth a lot. So first, I'll often be using this dot notation to denote absolute growth rates, absolute time derivatives. So x dot is the rate in absolute terms at which x is growing per unit time. When we just talk about the growth rate of some variable without specifying whether we mean the absolute or proportional growth rate, we'll basically always mean the proportional growth rate. That is the derivative of the thing over time divided by its level at that time. And it'll be written g sub x, or whatever the variable is. Of course, that itself can change over time. Then we can just write gxt. It can be helpful to see that the product of two variables grows in proportional terms at the sum of the growth rates of its components. Again, this will be really basic to very many of you, but just because we're going to see it so often, just to make sure, here's a quick intuition as to why that's true. Suppose that around some time t, the variables are growing at rates gx and gy respectively. Then locally, at least around t, x will be proportional to e to the gxt. Likewise, y proportional to e to the gyt. And so the product of the two things will be growing at rate gx plus gy here. Right? You just add up the exponents, and so xy is growing at rate gx plus gy. Now, I have, a list of rules that are kind of similar to this or that follow from it, and notes at the end of the slides on why they're true and how to prove them and develop intuition about them. Hopefully they're all straightforward enough, right? Growth rate of x over y will be growth rate of x minus the growth rate of y for the same reasons before. X to the alpha will grow at alpha times the growth rate of x, because x to the alpha is just x times x times x, alpha times, and so forth. Note also, this is maybe not quite as immediate, that the growth rate of a variable will be the absolute growth rate of its log. So to work out what that variable is at time t, given that you know what level it took at time 0 and you know the growth rates that it exhibited in between, you can say, okay, it's just going to be x0 times e to the integral of the growth rates between 0 and t. You can just take the log of both sides. So log x equals some constant plus this integral of the growth rates. And that makes it clear that the absolute growth rate of x will just be the growth rate at t, because that's the rate at which this integral is growing. And finally, helpful, but maybe most intuitive at all, kind of asymptotic rule. If you've got two variables growing at different rates, and or at least they're growing at variable rates, and one of in the limit they're growing at constant rates, and they're different from each other. The growth rate of the sum of the two will just be the maximum of the two. Now back to pulling rabbits out of hats. So suppose the population growth rate is fixed at 0 or something positive, so that by Caldor fact 1, the growth rate of output is constant, right? Fact 1 was that output per person is growing at a constant rate. But if the growth rate of population is also constant, then that means that output itself is growing constantly. Let S denote the saving rate, the fraction of output every period that's getting not consumed, but turned into capital for the future. And let D denote the rate of capital depreciation. The first thing to notice is that capital is going to grow in absolute terms like this. This will be the law of motion for capital. The rate at which we pile up more capital this year is what fraction of this year's output we save minus, the total amount of output we save, so the fraction we save times the quantity that we produced, minus the total amount of capital that depreciates, which will be the depreciation rate times the capital stock. That's the first thing to notice. The second thing is that by Caldor fact 3, if the capital to output ratio is staying constant, well, that means that capital and output have to be growing at the same rate all the time, right? To just keep them in constant proportion to each other. Now, taking this first line here and dividing through by k, we get that the growth rate of k, which is the same as the growth rate of y, equals this, which will equal that. And what this means is that if the depreciation rate is constant, then the savings rate must also be constant. And in fact, we can say what it'll be as well. It'll be, because we've got our G here, G, maybe I should have noted, is the common growth rate of output and capital. So G equals S y over k minus D. So rearranging, S is going to be G plus D divided by k, times k divided by y. And sure enough, we do observe, in very broad strokes over a very long time, a roughly constant savings rate. And this is compatible with roughly constant depreciation, which has long been sort of standardly observed. Capital depreciates at something on the order of 5 to 10% a year. Now, arguably, the capital depreciation rate is rising, maybe in part because higher tech equipment breaks more easily and or is rendered obsolete more quickly. So in a pretty extreme case, GPUs seem to only last about 3 years. But, most of the economy is not yet GPUs, though some days it looks like we're getting there. So, basically we've got constant depreciation rate, and the Caldor facts tell us that has to come with a constant savings rate. Okay, so what else do the facts imply? Given that we've established a constant savings rate, we can say something about people's utility. Consider an individual or a household that wants to maximize its utility, or in particular, the integral over time of its discounted flow utility at each time. Right, we thought about this problem yesterday a bit. let big R sub t denote the cumulative interest rate from time 0 to time t. If you put aside $1 now, how many do you get back, or how many in real terms do you get back t units of time later? If the household's saving optimally, it's indifferent on the margin between spending a bit more now and investing a bit more until time t and consuming it then, or spending it then. So by our first order condition, it's got to be that the marginal utility of consumption now at time 0 equals the marginal utility of consumption at time t times the number of units of consumption it'll actually be able to reap at time t by giving up a unit now, sending it to the future, times the discount factor at time t. So every time gets a multiple df that accounts for the fact that you might care less about utility in the future than utility today, or indeed more in principle. Now, this will tell us that if the household's consumption is growing at that common rate g, so its consumption is growing as fast as everyone else's, and if their investments are earning the standard interest rate, so it's not that people have access to private investment opportunities no one else does or anything like that, and if that's constant, we can just replace r sub t with e to the little rt, right? This is your constant interest rate, so cumulative interest from 0 to t will be e to the rt, and cumulative growth in consumption from 0 to t will be e to the gt. How do we know that consumption is growing at that typical, at rate g, since we've just established that output grows at that rate, not consumption? Well, that'll follow from the constant savings rate, because at every time, consumption is just going to equal 1 minus saving times output, right? So given constant s, growing y, you get growing c at the same rate. So this will hold. And we can say something about the df as well under a sort of mild condition on sort of consistency and rationality. So now suppose that discounting is time invariant, meaning that the schedule of discount factors from some time onward is independent of when you start. So if you draw out the curve of, let's say we normalize, we say that how much you like a util now is 1. How much do you like a util next year, the year after that, the year after that? If you draw out the shape of that curve, that'll look the same regardless of when you start. So your kind of psychology, your time preferences and so on, are not themselves changing over time. Next year always feels like next year. So given that time invariance, then it's got to be that your schedule of discount factors is exponential. So every further year into the future knocks a constant proportion off of how much you care about getting a util then. That's got to hold, or else you can sort of be continually ripped off. And the idea here is, let's say you deviated from that exponential form in some way so that the proportion, the discount that you put on a util next year relative to this year was different from between 4 years from now and 5 years from now. Let's say you care about next year 20% less than this year, but you currently care about year 5 the same as year 4. And someone who offered you the chance to to get a benefit now at the expense of next year, it's a mild expense, um, you're going to want to take that, but you're not going to want to take that between years 4 and 5. So someone, yeah, I mean, someone could offer the reverse, right? So someone could come to you today and offer you a small benefit in offer you a large benefit in year 5 at the cost of a small cost in year 4, and that'll seem appealing because you care about years 4 and 5 about the same. But once year 4 rolls around, you're discounting year 5 by a lot, by 20% relative to year 4, and so you're going to want to pay to undo this agreement that you entered into at time 0. And so you're back to where you started, but you just paid to enter into and then renege on this contract. So assuming that people learn not to do that, or at least the people with enough money to basically be setting interest rates know enough not to do that. Yeah, you're going to have this constant df alongside the constant r and the constant g. And this in turn will tell us about the shape of the utility function. Why? Well, recall from before when we were dealing with elasticities of substitution and in particular inverse elasticities of intertemporal substitution, that the marginal utility yeah, right. So, every time consumption rises by like 1%, the marginal utility of consumption is going to fall by eta times 1%, where eta is that inverse elasticity of intertemporal substitution. And eta can be flexible. It can vary depending on like how much consumption you're starting from. But this will always hold, or at least it'll always hold for like small values of t. It'll hold if you like differentiate with respect to t, you're end up gonna get this for t around 0. Just looking at line 14 there, if we know that r and d, if r and delta are constant interest rate by the Kaldor facts, constant delta by the time invariance and consistency assumptions, that means that eta is also going to have to be constant. Oh, the last ingredient is that G is also constant, as we've seen, because output's growing at a constant rate and the savings rate's constant, so consumption's growing constantly. See that? Eta has to be constant, and we know what it has to be. It has to be R minus delta divided by G. That is to say, people have to have isoelastic utility. That's going to be the only way to match the Kaldor facts and that rationality that we assumed. At least given, that the population is constant or growing at a constant rate. To better understand why this is and how this argument's working, I think a helpful exercise could be to say, well, let's say we've actually observed linearly growing consumption and not exponentially growing, as indeed some have argued recently. Because this long run, this first Kaldor fact, as I was saying, I think they've held up pretty well, but not precisely. And people point out the deviations. The capital share has risen a bit recently, but also the growth rates declined a bit recently in the developed world. And a paper from a few years ago argues that a better description of recent growth is as a constant linear rather than a slowing exponential. So if we buy that, we can say, likewise, what can we back out about what the utility function has to be to match a linear growth rate in consumption alongside a constant interest rate and a constant discount rate? take the time to do that. Um, if if the connection between the macroeconomic facts and the individual utility functions is not so clear. As for how to estimate what the variables are, in particular, what eta is, given that what eta and delta are, given that you observe interest rates and growth rates, standard thing to do would just be to run a regression and plot the interest rate on the growth rate. Of course, there's going to be a lot of noise, but you're going to run that regression. You're going to get some intercept, right? And some slope. And the intercept, what the interest rate is, even in a world with no growth, that'll just be the discount rate. And the slope will be eta. That will be how much the interest rate changes from year to year in responses to fluctuations in the growth rate. And when you do this exercise, or more sophisticated versions of it, where you also throw in 100 other potential determinants of the interest rate and so on, you typically end up estimating that intercept is around 2%. We'll discount the future at something like 2% a year, at least when making their big financial decisions. And that slope, that eta, is maybe something like 1.5. So this is what'll be generating the 5% interest rate we talked about before. Maybe 2% of it's driven by pure time preference, and then another 3% is driven by the fact that consumption is growing at 2% a year, and consumption is less valuable when you're richer because of this eta. There are all sorts of different approaches, but they do generally find an eta greater than 1. And note an important implication of that. Eta greater than 1 means that flow utility is upper bounded. So I'll be talking later about how I don't think that's the right lesson to draw. And I think it's a almost absurdly pessimistic conclusion that there's just this hard cap on utility per unit time, and we're just approaching that ceiling as consumption grows. I think that new inventions can raise the ceiling over time, and we can get better and better off. But within the context of a simple model like we're working with here, and which is used throughout, I think, a considerable majority of macroeconomics, including macroeconomics of AI, you get a eta greater than 1, and the implication is that flow utility has an upper bound. Okay, now let's take a bit of a detour to think about the AK model. This is a model, or the model, of a world with only one factor of production, capital, so that given constant returns to scale, output is just proportional to capital. A here will take a slightly different interpretation from before. It'll be capital productivity net of depreciation. So it's how much output a unit of capital produces after siphoning off whatever you need to repair the 10% or whatever of that unit of capital that depreciated over the course of the year. We could split A into the capital productivity before depreciation and the depreciation component, but this would make no substantive difference and just makes things simpler to work with it this way. What's the interest rate in this world? Well, it's the marginal product of capital, as always, so it's A. A really clear way to see that, let's say you put aside little k units of capital. Well, next year you should have 1 plus AT times as much capital. So that extra that you earned is just going to be proportional to what you invested, and the proportion will be A. So given a constant interest rate, given that we maintain Caldor fact 2, big A, the productivity of capital, has to be constant in this world. An AK economy fitting that Caldor fact is going to be constant, and it's going to deliver constant growth as well. Another approach we could have taken is to say, let's say we also had a constant savings rate and we have constant growth. then you've got to have constant A. So in an AK world, exponential growth, given constant saving, as I was saying, implies no technological development. Output growth has to all be about capital accumulation. Some observations about this model are, first, there's no spillovers in it, positive or negative. Like the quantity of capital, or of anything, but capital is really all there is. The quantity of it has no effect on the marginal product of capital. We don't have a dynamic with diminishing returns to capital, where the more you have, the lower the marginal product. And we also don't have some other factor that's being augmented, that's being complemented by the existence of more capital. And so we can think about households sort of like separate farms, deciding side by side how much of the rice they produced last year to consume and how much to plant for next year. And how much they get next year, it just depends on, it's just proportional to how much they're planting. It does not describe a realistic economy. Of course, there's no labor in it. And even though there is a technology term, there's no room for it to be driving growth, at least under realistic conditions that have held in the past of constant growth, constant interest rate. It might, though, roughly describe the sort of microeconomic conditions faced by a household that's living off passive investments, or a philanthropist or something, a foundation that basically is facing an interest rate that's not going to change when it decides how much it saves. How much it spends this year just changes how much capital it has left over to invest and have more to spend in the future. So it's sort of locally living in an AK world. So that's why it can be useful to think through the logic of AK growth, capital only growth, somewhat carefully. It'll also be helpful, of course, because we're going to be thinking about what will change when we actually get to full automation or approach full automation, where output is just a function of capital. But that's putting the cart before the horse. For now, let's just think about how capital accumulation and saving would work in an AK world with constant technology. So our law of capital motion will just be this thing here, right? Because we're incorporating depreciation into that A term. So how much more capital we pile up this year is just the fraction of output that we save. And dividing both sides by K, we get that the growth rate of capital is just the savings rate times A. Now, suppose a population size is fixed, then, meaning that like output per person is growing at the same rate as output and so on. With constant A, the growth rate of capital will just equal the growth rate of output, because y equals AK. And to satisfy that first Caldor fact of constant growth in output per person, or equivalently constant growth in output, we should observe constant GK and S in this model. And so, we're gonna ask whether we do observe that, given isoelastic utility. So given that people have the utility that they seem to have in the real world, not in an AK world, suppose they have that in the AK world, will we get the constant savings rate and the resulting constant growth rate of capital that we need to maintain constant growth in output? And we'll see that we do. So let's think through optimal saving. Again, this is optimal saving in an AK world, but it's also just optimal saving in general for any entity that's just living off its capital and not so big that it can really shift the interest rate around. By that Euler equation, that first order condition, optimal saving has to maintain this indifference between consuming a little more now, getting this much marginal utility now, and investing until time t on the margin and getting this much marginal utility per dollar, e to the RT dollars, and discounting it by e to the negative delta t. And rearranging this, an optimal saving path will maintain exponential growth of consumption. And the growth rate will be this, r minus delta over eta, for raising both sides to the 1 over eta, and then we're just flipping the CT and the C0, because they're each is raised by -1, and then we multiply both sides. Subjecting this to the budget constraint, the present discounted value of all your spending has to equal your current capital stock, right? So if you imagine taking your capital stock now and cutting it up into infinite slices, one of which you'll consume today, one of which is put aside to grow until tomorrow to be consumed then, a third, presumably smaller, will be put aside for 2 years from now, and so on. And so, the crumbs get cut up ever more finely as you go around the pie, but you've got some crumb left for every period in the future. The size of the crumb will be the amount that you actually get to consume at time t, discounted by the interest that you earned in the meantime. And so integrating from 0 to infinity, that is integrating around the pie, you're going to get your current capital stock. And pulling out the C0 and integrating, we get that you're always consuming a constant fraction of your capital stock. And this will be the fraction. So the capital stock will be growing at some constant rate along with consumption, because if consumption is growing at a constant rate and consumption is always the same proportion of the contemporaneous capital stock, then the capital stock is also growing at that rate. And output will be growing at that rate. And that rate will be this exponent here, r minus delta over eta. And the savings rate, which we saw before, will just be the growth rate divided by a. That'll be r minus delta over r eta. You can see that from the fact that consumption at some time is going to be the fraction of income not saved. And income is just the interest rate times capital, and the fraction not saved is 1 minus s. So you can just put r times 1 minus s times k0 will equal this term here, r eta minus r plus delta over eta times k0. As an aside, we can ask, it's often be important to ask, when raising the interest rate raises versus lowers consumption. You'll see there's two effects at play here. A higher interest rate means that you're richer. So if you consume the same amount at any point in time, you're not richer kind of immediately, right? But your prospects are better. So if you save the same amount at every point in time, but the interest rate's higher, then you're going to be not changing your consumption now, but you're going to be consuming more and more in the future. And one thing you might want to do is take advantage of that by consuming a bit more now. So the interest rate goes up, you consume more now, you save less, and you take some of those, some of that extra wealth provided by the higher interest rate up front. On the other hand, if you don't care so much about when you consume, or about kind of maintaining a roughly constant level of consumption over time, but like extra consumption counts almost as much for you in the future, even though you'll be way richer. A higher interest rate could give you a reason to cut back on consumption now, because if you invest, you'll be consuming so much more in the future. And as we can see from the formula, it all depends on whether eta is greater or less than 1, right? just dividing through by eta, you've got r times eta minus 1 in the numerator. Yeah, you don't need to divide at all, actually. Eta minus 1 is the coefficient on r in the numerator. And that'll be positive if eta is greater than 1. So if eta is greater than 1, that is if consumption is not so substitutable between periods, if the inverse elasticity of substitution is greater than 1, then a higher interest rate makes you consume more now. You want to, you don't care so much about getting richer still in the future. So when the interest rate goes up, you just take that largely in the form of increased consumption now, and you save less for the future. And if eta is less than 1, like if it's close to linear, your utility is close to linear, then a higher interest rate gives you this opportunity to defer your consumption to a time when you'll be, it can accrue lots of that high interest. Now, note that what we found on the previous slide was actually just an optimal saving plan if one exists, but one doesn't necessarily exist. In particular, if people are too patient, if the discount rate is not higher than this r times 1 minus eta term, then this numerator here, and therefore the whole expression for the fraction of your capital that you consume each period, this will be 0 or negative. And that's clearly wrong. In fact, you can see that it's wrong just from the fact that consuming 0 or negative forever will violate the condition that you consume your budget. And what's going on is that when this condition is violated, when people are too patient, there just is no optimal saving plan. The thing is, however much you save, it'll always be better to save a little bit more until you save everything, and that does no good at all because you never get to consume. I think this is just a technicality in practice, but it's just something to make sure is satisfied. And note that you can be perfectly patient and still satisfy this condition. As long as eta is greater than 1, which, as we've seen, is typically what is found, and the interest rate's positive, then you have a 0 on the left and you have something negative on the right, and there is an optimal saving plan. Now, outside an AK economy, this generally won't be an issue because if you did actually try to save a lot forever, you would eventually push down the interest rate because there's decreasing returns to capital in isolation. Think about the Cobb-Douglas case, for instance. Let's say the exponent, little a, on capital is 1/2. And as the quantity of capital rises, the marginal product falls. In particular, if capital is growing more quickly than effective labor, the marginal product of capital is going to fall. And so the interest rate will eventually reverse the inequality for you, and you're going to want to start consuming. But in an AK world, you need to impose some condition to ensure that an optimal saving plan exists. Okay, so that's an AK world and optimal saving more generally. Now we'll get back to pulling one last rabbit out of the hat about what the Caldor facts imply for the economy at large. So to start with, let's work out the formula for the capital share in a CES economy. Okay, so we've got our CES and, as usual, CRS production function. It looks like that. The capital share looks like that, expression 25. You can differentiate on your own, but yeah, the idea is you just you pull down a 1 over rho minus 1, and then on the outside you get little a times a to the rho k to the rho minus 1, but the rho you pulled down cancels with the 1 over rho you pulled down from the square brackets, and that's the marginal product of capital. Multiply that by the quantity of capital and divide through by y, because we're getting the capital share. And this is what it works out to. So if rho is negative, if the factors are gross complements, as usual, then increases to A will lower the capital share. And this is precisely for the reason that when the factors are gross complements, increases to K lower the capital share. It's the two things are always multiplying each other, so they'll always have the same effect on this, on the factor share. More effective more capital augmenting technology, just like more capital, means more effective capital. When we have more effective capital, you're lowering the marginal product of it by more than you're raising the quantity, at least in relative terms, relative to effective labor, and so you're lowering the capital share. And likewise, if rho is greater than 0, then increases to A, more effective capital, greater capital share. Okay, so we're thinking about the impact of changing A on the capital share. But remember the Kaldor fact that the capital share is constant. Okay? Uzawa's theorem tells us that if we're looking at some data over time, over the path of wages and interest rates and output, we can always match the Kaldor facts by positing a production function in which A is fixed over time, so only B grows. And in fact, typically, we're going to have to assume this. So the proof is, well, in the CES case, a really simple proof just follows from the formula on the previous slide. Since the capital to output ratio is fixed by Kaldor fact 3, and this whole thing is fixed, the capital share is fixed by Kaldor fact 2, well, it's got to be that big A is also fixed. If it varied, the capital share would change. Again, the theorem is that this holds for any constant returns to scale production function, not just a CES one. But we won't go through it. Hopefully the intuition is clear from the CES case. The one edge case in which we don't have to assume that all technological, or rather all factor augmenting technological change is labor augmenting, is the edge case is the Cobb-Douglas case, the rho equals 0 case. And why is that? Well, in that case, as we've seen, it doesn't matter whether you call factor augmenting technology labor augmenting or capital augmenting. You can just talk about TFP. So in this case, the A is redundant. You can say that it grows. You can sort of split technological progress into some growth in A and some growth in B, or whatever you like. This in turn means that given a constant returns to scale production function and the Kaldor facts, and the very mild assumption that output is increasing in both its arguments, effective capital and effective labor, then output, effective capital, and effective labor all have to be growing at the same rate. When this happens, this is called balanced growth. So this is what we seem to have observed roughly in the past. Proof by contradiction is, suppose the arguments of our function, our effective capital and labor, start out equaling some values, AK and BL. And suppose that AK and BL don't grow at the same rate. Suppose that after some time, effective capital is MAK and effective labor is NBL for different values of M and N. Uzawa's theorem tells us that A was constant, so K got multiplied by M. And the constant returns to scale assumption and the assumption that output's increasing in each argument tell us that overall output had to be multiplied by something strictly in between M and N. It's got to be in between because, on one extreme, let's say that both the arguments were multiplied by the max of M and N, then Y would as well. That's just constant returns to scale, right? And likewise, if they were both multiplied by the minimum, Y would as well. But we know that it grew by more than the minimum because it's increasing in both arguments. And so, you can think about multiplying both factors by the minimum and then increasing just the other one. And likewise, we know it grew by less than the maximum by the strictly increasing assumption because you're decreasing the other. So output would have grown by a different amount as capital, right? Whatever's in between M and N, that's different from M. And we know that capital was multiplied by M. This means that the capital to output ratio changed in violation of Caldor Fact 3. So to maintain these assumptions, you've got to have these three expressions all growing at the same rate. In particular, Y, K, and BL all have to grow at the same rate by Uzawa. All right. So to recap, we've introduced the arguments for taking as a good approximation that production exhibits constant returns to scale. We found that given constant returns to scale, you can talk about competitive markets, right? Factors getting paid their marginal products, but absent constant returns to scale, you can't. This is all from Euler's homogeneous function theorem. We talked about a firm's problem of allocating resources, allocating its budget to maximize production, how that's analogous to budgeting to maximize utility. We also kind of thought in reverse about given stocks of the factors, how the prices have to change when the stocks change to maintain that supply equals that demand equals that posited supply of the factors. We talked about what factor augmenting technology means and what TFP and TFP growth mean. And then we pulled a bunch of rabbits out of hats. We found that given these three Caldor facts, and given that population growth is roughly constant, at least over the time scale that we're thinking about, and given that people discount exponentially and aren't so patient that that there's no optimal savings rate. Given those background assumptions, it's got to be that people have isoelastic utility. It's got to be that the Ramsey formula holds. The interest rate exhibits that relationship between the discount and growth rates and the shape of the utility function. And it's got to be that the savings rate is constant. It's also got to be that the capital share is constant. I should have added that to the list. Apologies. But that was right at the beginning. When we were introducing the stylized facts, we observed that just by multiplying facts 2 and 3, you get a constant capital share. Then finally, adding that mild assumption that production is strictly increasing in both its arguments, we found that, I did put this at the end here. You get constant factor shares. I think, you don't actually need the increasingness for that. But anyway, that follows from the above. The interesting thing is that we know that growth has to be driven by growth in labor augmenting technology and not by growth in capital augmenting technology. That was Uzawa's theorem.